Let's talk a little today about wave interference. This basically means just the way that two waves can interact. So let's imagine that we have a wave like this, and then there's another wave also up in the above direction. Maybe this wave is moving this way, and this wave is moving this way. How are they going to interact? Well, after some time, when they meet each other, they're actually going to combine and make a bigger wave. This is called constructive interference, where two waves meet and they both have the same displacement, or the same direction of displacement, either above or below the medium, and they kind of just add together. Now they're actually, afterwards, these actually will continue on. We'll have the smaller one, and then the other one, and then they'll still be moving apart from each other. But when they meet, they sort of add together because in the same direction. Now, that's called constructive interference. A similar thing happens when one's up and one's down. So if we've got a situation where we have a wave down like this, and another one up like this, and they're moving towards each other just like we talked about, when they get together, we're going to end up with a much less severe wave down, because here they actually subtract, and this is called destructive interference, where they actually cancel each other out partially. So it's pretty straightforward, and they basically just add. If the amplitude of this was -10 and this was 4, this would be -6. It's just straight up addition. Okay, so you're not really going to have any problems on this on your classwork today. This is an easy idea, but this will be on your test. There will be some multiple choice questions about constructive or destructive interference, and if you just remember this simple idea that if they're in the same direction they add together, and if they're opposite directions they subtract and sort of cancel, you'll get it. It's an easy thing. It's just how waves interact with each other. Okay, so let's talk about waves at boundaries. So let's imagine that we have a rope tied to a pole in such a way that the rope can move freely up and down the pole. And I'm actually going to borrow an image from your textbook to help me talk about this. So here we see the rope's tied around a pole, and we can freely slide it up and down. We assume there's no friction there. If we make a wave in the rope, it'll travel down the rope, and it'll make the rope slide up the pole, then the rope will slide back down the pole, and it'll reflect the wave right back in the opposite direction with the same magnitude. It just reflects it. It just bounces right back. It wiggles the end of the rope goes back to where it was, and it gets reflected back in that same direction. It's pretty straightforward. This is when one end of the rope is free to move back and forth, up and down. Not left and right, that messes things up, but if it's free to move up and down, that's the way that that works. Now, compare that with this. This time the end of the rope is fixed. It cannot move up and down with the pole. This time we see the wave, and here it's going towards the pole. It hits the pole, and then the wave reflects, but notice that this time it is inverted. So when one end is free to move back and forth, it reflects, it is the same as it was. When one end is fixed, it still reflects, but it is inverted. And that's a subtle thing that you will see on tests. It's something you do need to know about the interaction of waves at boundaries. Alright, well, we talked a little bit about sound last time, and there's a supplementary video that I've posted about the Doppler effect that I want you to watch. But I also want to talk a little bit about the Doppler effect. Now, before we talk too much about the Doppler effect, we have to realize that there are a couple of things going on. When we hear a sound, it has a pitch. And that pitch is directly related to its frequency. A higher pitch means a higher frequency. So a low sound has a very low frequency. A high pitch, a high sound has a much higher frequency. So why does this matter? Now, what the Doppler effect is the idea that motion and waves cause some funny things to happen. The most common idea with the Doppler effect is there's someone standing on the side of the road. And again, this will be illustrated in the video. I'll also have you watch. But you're standing on the side of the road, and a motorcycle goes by. There's the motorcycle. And as it goes by you, you hear meow. Okay, you don't just hear it goes meow. That's the Doppler effect. And that's caused by the fact that the pitch of the motor doesn't change. Like if you're standing next to the motorcycle while it's running, it's just going to have a certain sound. So while the motorcycle is still, the sound waves coming off of it are evenly spaced. Well, as evenly spaced as I can draw them. Okay? But when the motorcycle is moving towards you, it's moving forward, so that's causing its sound waves to get compressed closer and closer together. So you actually hear a higher pitched sound than the motorcycle's making. Same thing, once it's past you, it's moving away from you. And so its sound waves are farther and farther apart. That's why you hear a lower pitched sound as it's moving away from you. That's the Doppler effect. It also works for light. In astronomy, you'll talk about the Doppler shift. Things moving towards you look one color, away from you look another color. That's how scientists have theorized about the Big Bang and which galaxies are moving towards each other and which ones are moving away from each other and that sort of thing. So generally this is true about waves. If you're moving towards something, the perceived frequency of a wave will be higher. If something's moving away from you, the perceived frequency of the wave will be lower. That's the Doppler effect. So you need to know that. You need to be able to talk about that and answer a question about that. Now, waves can have an attribute called intensity. Sound waves are what we're going to talk about today, but any wave, any longitudinal wave, a spherical wave, can have it. Anything that radiates equally in all directions. Anyway, and you've probably felt it before if you've stood close to like a guitar amplifier or something. You can actually feel the sound. And what you're feeling is the energy transfer that the sound wave makes when it touches the molecules in the air and then the molecules in your skin. And so that's why you can actually feel the sound. And there's a very simple formula for intensity. It is intensity, which doesn't really have a variable, just intensity, equals P, which is power, over 4 pi r squared. So intensity is the power divided by 4 pi r squared. Now, really, more simply, it's just the change in energy, because remember, power is the change in energy over the change in time, or over a time interval, over the area. Remember, 4 pi r squared is the area of a sphere. So the power is evenly divided around the whole area, around the whole sphere, because sound radiates in a sphere. Yeah, that's what's really happening. But the functional formula that we're going to be using will be this one. P equals 4 pi r squared. So I'm not going to do any examples because this is a really straightforward formula. They'll either give you intensity, power, or distance, or I suppose I could really throw like a curveball in there and give you like energy and ask for time or something. But I probably won't. Probably will just give you either power, radius, which is distance from the thing that makes the sound, or intensity, and ask you to find the other one. So obviously you're going to be putting this over 1 and cross multiplying and doing all that good business. Lots of good algebra for us to do there. So that's it for today. Next time we'll get into more with light and refraction and all that good stuff. But that kind of wraps it up for what we're going to be doing with sound in here for now.